Hi, welcome to this presentation on a few applications of ordinary differential equations. This is the abstract of my presentation. Many problems in modern science and engineering can be modeled as differential equations. These models are widely used to study the growth of organisms, biomedical and chemical reactions, variation of populations, and the spread of epidemics. In this presentation, a few such applications of ordinary differential equations are discussed. So first of all, we'll see what an ordinary differential equation is. An ordinary differential equation, which is also called an ODE, is an equation involving an independent variable and a dependent variable and the derivatives of the dependent variable with respect to the independent variable. Most commonly, we take the independent variable to be x and the dependent variable to be y. So accordingly, a differential equation, an ordinary differential equation, involves x, which is an independent variable, y, which is a dependent variable, and the derivatives of y with respect to x. The general solution of an ordinary differential equation is a function y equals y of x or g of x comma y equals c, which satisfies it. That means to say that if you are able to find a function y equals y of x or a function of x and y equals some constant which satisfies a differential equation, then it is said to be the general solution of the given ODE. In particular, a first order ordinary differential equation is of the form dy by dx equals f of x comma y, and an initial value problem, which is also called an IVP, is a first order ordinary differential equation along with an initial condition. That means we have a differential equation dy by dx equals f of x comma y, and with that we are also going to have a condition which is of the form y of x naught equals y naught, which means that at the value x equals y x naught, the value y will be y naught, the value of y will be y naught, right? This is what is called an initial value problem. And now we'll look at a few applications. In fact, I'm going to discuss exactly two applications of first order ordinary differential equations in this presentation. Here the first application is Newton's law of cooling. This is a very important law that is studied in chemistry. The statement of which is as follows: the rate at which the temperature of a body decreases is proportional to the temperature difference between the body and its environment. What does this mean? It means that the temperature of a body decreases and the rate at which the temperature of a body decreases. So there is a particular object or a body which is brought in the vicinity of a certain environment, and suppose the temperature of the environment is much lesser than the temperature of the body, then the statement is that the rate at which the temperature of the body decreases is proportional to the temperature difference between the body and its environment. Now, to understand this in terms of mathematical expression, we denote the temperature of the body to be capital T, and we take TE to be the temperature of the environment, and we're going to take capital T as the temperature of the body at any time t. Then the rate at which the temperature decreases or increases is denoted by dt by dt. This gives the change of temperature with respect to time. So according to the statement, dt by dt is proportional to the temperature difference between the body and its environment, and the temperature is supposed to decrease. So we are going to have a minus sign, and this will be the proportionality constant k into T minus T. T minus T gives you the difference of temperature between the body and the environment. So dt by dt is given by minus k into T minus T, is what the Newton's law of cooling says in terms of simple mathematical expression. Now, if you look at this equation 1, this is a simple first order ordinary differential equation in capital T and small t, which is easily in variable separable form. You can separate the variables very easily. Because you can separate the variables very easily, solving this becomes very easy. So take t minus t to the denominator on the left hand side, and if you send dt to the right hand side and integrate straight away, you would see that the solution of this differential equation will be log of t minus te equals minus kt plus a, where a is the constant of integration. Now this can be simplified further by taking anti-log on both the sides and simplifying, and that will give us capital T equals capital TE plus B into e to the power minus kt. Now this is the solution of the differential equation that we have discussed earlier, and this is supposed to be interpreted in terms of the problem that is being considered. Now capital T, as we know, is the temperature of the body. It is given by TE, which is the temperature of the environment, plus B into e to the power minus kt. Now to understand this, we'll look at the plot of this particular expression. So we're going to have the x-axis to be the time t and the y-axis to be the temperature capital T of the body. Then according to this equation, this expression, if you try to plot, because we are having an exponential function which is having a minus sign, it means that the graph is going to be an exponentially decreasing function. So as we can see from the graph, capital T starts from T0, okay, and it keeps on decreasing exponentially. T0 is the initial temperature of the body, right, at time t equals 0, as we can see here. So as time progresses, the temperature of the body keeps decreasing and decreasing and decreasing, and is going to reach capital TE as time becomes larger and larger. So as the time approaches infinity, the temperature of the body will be equal to the temperature of the environment, is what this says. And not just that, the temperature of the body decreases exponentially is also the interpretation of this. So as we can see, capital T decreases exponentially as small t increases. Capital T decreases exponentially as small t increases, and capital T approaches capital TE as t tends to infinity. So this is how we can understand this particular problem using or solving the corresponding differential equation. So this is one application that I wanted to discuss. The other application is actually a very famous model which is studied in the population dynamics. It is known as the Lotka Volterra predator-prey model. So the Lotka Volterra model is a simple mathematical model that demonstrates the dynamics of the population of a predator and its prey in an environment subject to certain assumptions described as follows. So what is this model? It is going to be a mathematical model which makes us understand the dynamics of the population of a predator. Predator is an animal which hunts, and a prey is an animal which is getting hunted by the predator. Okay, so we are trying to understand the dynamics of the population of a predator and prey in an environment. That means we are going to understand how the population of a predator and a prey changes in a certain environment, and that is being done keeping some assumptions in mind. In fact, these assumptions are made by Lotka and Volterra independently. These were the assumptions that were made by them, and the model was constructed. Therefore, this model is named after them. Okay, now we will consider two species. One of the species is a predator. For our discussion from now on, we'll assume that the predators are foxes, and the other species is going to be a prey, which is taken to be a rabbit in this particular discussion. So we have the predator as foxes and we have the prey as rabbits, and we are going to assume that the population sizes of the foxes is going to be y of t, and the population size of the prey, which is rabbits, is going to be x of t. So at a reference time t, y of t is greater than or equal to 0 and x of t is greater than or equal to 0. Now the assumptions that we are going to make are as follows. The first assumption is that we assume that the population of the prey finds sufficient food at all times. That means the rabbits have enough food to sustain or survive for any time whatsoever. The food supply of the predator population depends entirely on the size of the prey population. This means to say that foxes eat only rabbits. This is a very important assumption that we are making. So we are assuming that foxes depend only on rabbits and they do not depend on anything else for their food. We also assume that the environment does not favor in either way any species during the study. What does this mean? This means that the population of the foxes and rabbits are dependent on each other, and the environment will not play any role in the variation of their populations. Okay? The next assumption is that the predators can assume infinite quantities of prey. That means foxes can eat any number of rabbits. Okay? Then the prey population is proportional to its population size. What does this mean? Prey population means the population of rabbits. As long as the number of rabbits is more, accordingly, because they have enough food to survive, the growth of the population of rabbits is going to be increasing, right? So the rate of change of population of the rabbits is directly proportional to its population size. It is what it means. Now that is expressed by this expression, dx by dt proportional to x. Dx by dt gives you the rate of change of the population of rabbits. It is directly proportional to x is what it means. Fine. Another thing is that the population automatically, it grows exponentially if unchecked. That means if there is no other factor and the populations are not the rabbits are not being consumed, then the population of the rabbits is going to grow exponentially. Okay, yeah, this expression is going to be very important for the further discussion. Similarly, the predator population shrinks at a rate proportional to its size. Now, what does this mean? The population of foxes, if you look at it, more the number of foxes, lesser the food, right? Because there is more competition and you will not get enough rabbits to eat. So accordingly, the population of the foxes, it will not increase according to the number of foxes that is there. So the rate of change of population of foxes is minus into the actual population of foxes, because it shrinks. Whenever there is a shrinking happening or whenever the population is decreasing, we need to have a minus sign, and when there is a growth, we are going to have a plus sign. So dy by dt will be proportional to minus y. Okay. The next assumption, the prey population shrinks at a rate proportional to the size of the product of the prey and predator population. Now what do you mean by the product of the prey and predator population? The product simply means that there is an interaction between the predator and prey. Interaction means the rabbits and foxes are coming, they're getting confronted. So whenever foxes and rabbits come together, automatically foxes eat rabbits, and because foxes eat rabbits, the population of rabbits is going to decrease. The rate of change of population of rabbits is going to be proportional to minus x into y is what it means. Here x into y indicates an interaction between the population of rabbits and the population of foxes. So dx by dt will be proportional to minus xy. Okay. Similarly, whenever such an interaction happens, whenever rabbits and foxes come together, automatically foxes eat rabbits, and because foxes eat rabbits and they survive, it means to say that the predator population, that means the population of foxes, it grows at a rate proportional to the size of the product of the prey and predator population. So dy by dt will be proportional to plus xy. So these are four expressions which are to be remembered. Dx by dt will be proportional to x, dy by dt will be proportional to minus y, because here there is a growth, here it is decreasing, the shrinking is happening. Likewise, dx by dt will be proportional to minus xy, because the interaction will decrease the population of rabbits and it will increase the population of foxes. So these are the four expressions that we have. Now putting these things together in terms of an equation using proportionality constants, we see that dx by dt equals alpha into x minus beta into xy, where alpha and beta are proportionality constants, and dy by dt will be minus gamma y plus delta xy, where gamma and delta are again constant of proportionality. Okay. Again, I want you to understand why this is plus and minus here and minus and plus here. Dx by dt is directly proportional to x, and dx by dt is proportional to minus xy. So we are going to have a minus sign here and a plus sign here for dx by dt. And for dy by dt, dy by dt is proportional to minus y and dy by dt is proportional to xy. So dy by dt will be equal to minus gamma y plus delta xy. So as I mentioned earlier, alpha, beta, gamma and delta are constants of proportionality. Now these two equations 3 and 4 taken together are going to represent a simultaneous differential equation in x, y and t. Right? Now before going for solving this simultaneous differential equation, we are going to look at a special type of solution called equilibrium solution. So what do you mean by an equilibrium solution? Equilibrium solution is the case when the populations remain invariant. That means the population remain unchanged. Now X is a population of rabbits and Y is a population of foxes. When will they remain unchanged? When there is no change in the populations. That means the rate of change of X with respect to T and Y with respect to T should be 0. There should be no change whatsoever, right? So that equilibrium solution is obtained when we take dy by dt equal to 0 and dx by dt equal to 0. And that means we are supposed to take alpha x minus beta xy equal to 0 and minus gamma y plus delta xy equal to 0. Right? Now these two together are basically two simultaneous equations. Solving them will give us two solutions, namely x equal to 0, y equal to 0 and x equals gamma by delta and y equals alpha by beta. Okay, now what do you mean by this? In terms of interpretation, this means that when x is 0 and y is 0, that means when there is no fox and when there is no rabbit, then the population will remain the same. That means the two species will continue to be extinct if they are already extinct. If there is no rabbit and if there is no fox, automatically there will be no growth of there will be no population of fox or rabbits changing, right? So when x and y are 0, then they will remain extinct as they are. And in the second case, when x is gamma by delta and y is alpha by beta, that means when the population of rabbits is gamma by delta and the population of the predators is alpha by beta, then their population will remain the same until an external factor comes into picture. That means if x takes a value gamma by delta and y takes a value alpha by beta, from then on the population of both the rabbits and foxes will remain as it is, irrespective of the interaction between them, and this will remain as it is as long as an external factor does not come into picture. So once an external factor comes into picture, only then this equilibrium will be disturbed. Okay, now this is a special solution that we have discussed. Now we are going to look for the general solution of this particular problem. So as we have already seen, these are the two expressions that we have. Putting together is going to give you a simultaneous differential equation. Now to solve this, we are going to convert this into an ordinary differential equation in y and x. That can be done by dividing one expression by the other. So dy by dx is going to give us, as we can see here, y can be taken common here, so y into minus gamma plus delta x, and here x can be taken common, that will give us alpha minus beta y. Now if you look at this, this is once again a simple ordinary differential equation in x and y, and once again this is also in variable separable form if you look at it carefully. So solving this can be done very easily by separating the x and y terms. So taking y terms to one side and x terms to the other side and integrating is going to give us this as a solution, which on simplification will give you this as the general solution, where c is the constant of integration. So the general solution is gamma into log x minus delta x plus alpha into log y minus beta y equals c, where alpha, beta, gamma and delta are the constants of proportionality. Okay, now this is a general solution. Now using this general solution, we are supposed to understand the population dynamics. Now for that to be done, we'll try to plot this for various values of c. Okay, now for that to be done, we'll also have to fix these constants of proportionality, alpha, beta, gamma and delta. So what we are going to do here is, we are going to choose alpha, beta and gamma and delta to be some certain values. In this particular discussion, I have chosen alpha to be 3, beta to be 1, gamma to be 2 and delta to be half. So if we choose these as alpha values of alpha, beta, gamma and delta, we are going to see that the graph of the solution is going to be this for various values of c. So as we can see here, each of these plots is basically a closed curve, closed contour, and we have taken the x-axis to be the prey and the y-axis to be the predator. So this is going to be the plot of the given function for various values of c for specific values of alpha, beta, gamma and delta. Now how do we interpret this solution? Yeah, as we can see here, each of these is a closed contour, and we can understand four different natures here in terms of the populations. Now when we start with this position, which is the case 1, as we can see here the population of the predator is pretty low. The population of rabbits is very much low here, and because the population, sorry, it's not the rabbits, it's the population of the foxes, I'm sorry. So the population of the foxes is very much low here, and because the population of the foxes is low, automatically, because there is no hunting that is going to happen, because not much of hunting is going to happen, the population of rabbits is going to increase for a certain period of time up to this particular point. Okay, so as long as the population of the foxes is low, the population of rabbits is going to increase for a certain time. And when it comes to this position, as we can see here, at this point the population of the rabbits is high, and because the population of the rabbits is high, automatically there is going to be a growth in the population of foxes. So from this point onwards, as we can see here, the population of foxes will grow and grow, and it will grow on up to this particular point, case 3. And in this particular case, what has happened, the population of the foxes has become very much high. And once the population of foxes is high, then what will happen, they start hunting more rabbits, and more hunting happens implies that the population of rabbits is going to decrease from this particular point onwards. So the number of rabbits is going to decrease for again a certain period of time up to this particular point. And in this case, case 4, what happens, at this particular point the population of the rabbits is low. So because of the population of the rabbits is low, what will happen, the population of foxes also starts decreasing, and it will come back to this particular position 1, case 1, and it repeats once again. So this particular pattern is going to go on and on and on for any amount of time, any period of time. And there is one more point that has to be observed. The center of all these is going to be this equilibrium position, which is already discussed as gamma by delta, comma alpha by beta. Right? So this is how the populations of the rabbits and foxes keep changing for any time t. Okay, so I'm talking about that itself as observation here. So the contour plots make periodic orbits around gamma by delta, comma alpha by beta, such that when the predator population is low, the prey population grows. When the population of foxes is low, the population of rabbits, it keeps on increasing. And when the population of rabbits reaches a very large position, when it becomes very much high, the predator population grows. And when the predator population is high, the prey population shrinks. And when the prey population has reached a lower level, the predator population also starts shrinking. It will reach the first case. And this is going to happen periodically for any period or for any time t. So this gives the relation between the predator and prey model using the Lotka Volterra predator-prey model. Right? Fine. So with this, I'm going to conclude with this presentation. So as we have seen, in terms of these two applications, differential equations play a very vital role in addressing many problems in the physical world. Problems of different nature can be modeled into a common differential equation, which in turn provides a common solution to each of these problems, varying only in interpretation. What does this mean? This means that we have so many different problems of different nature. As we saw in the previous two applications, both were two different problems altogether, but ultimately both gave us a simple ordinary differential equation, variable separable form. So they are going to give us a common differential equation whose solution can be accordingly interpreted based on the actual problem in the real world. Okay, involving, this is another important observation which I wanted to mention here. Involving more parameters and constraints in modeling the problem leads to differential equations which are more challenging in nature. See, here we have made so many assumptions which has ultimately given us a simple model for the prey-predator model. So if we involve more parameters and more constraints, the differential equations that we are going to get are going to be more complex in nature, and the solving of them also will become very, very difficult. In fact, many such differential equations cannot be solved in analytical methods. There we'll have to go for numerical methods. So to conclude, solving differential equations is going to be central and going to be very important in studying various problems in modern science and engineering. With this, I'm going to conclude with my presentation. Thank you for the patient listening. Get back to me if you have any queries. Thank you.